Welcome to topic number 13 in Richard James Mathematics Resources. This one has to do with decimal places, standard form, and significant figures. Writing a number to a specified number of significant figures or decimal places is merely making an approximation. The need for approximations arises from many circumstances. An irrational number has an infinite number of decimal places. Recurring decimals are also infinite. An answer may require a certain number of digits, and the advent of computer with limited space allocation storage variables also make use of approximations. One vital but often neglected feature of approximation is its attempt to preserve as much as possible the value of the original. This can be seen especially in rounding to significant figures in which trailing zeros are discarded in approximating a whole number. Placeholding zeros should be used so that the order or value or relative size, whether it is hundreds, thousands, tens of thousands, or the size of a number, is preserved. Making approximations is a simple task. Most times, only the silly mistakes and negligence prevent students from getting the correct answer. We're going to be looking at leading and trailing zeros. Leading zeros, that is, zeros that are to the left of whole numbers, bear no significance on the value of the number and may be discarded. They also do not act as placeholders at any time. So we have a number right here with two leading zeros. Of course, they may be discarded and the number may be written as 64,825. And of course, that one has three leading zeros and they also may be left off. And the answer is 563.97. The following statement pertains to numbers that have only a single zero before the decimal point. If they have zeros between the point and the non-zero digits, then those zeros have no significance other than placeholders. They will have significance only when counting the number of decimal places. So let us look at those numbers. Notice that they have zeros between the point, the decimal point, and the numbers, the non-zero digits here. And of course, in front of the point or to the left of the point, we have a zero. So all of those zeros that we have there contribute. The highlighted zeros have no significance with the exception of adding to the number of decimal places. If a decimal fraction has only a single zero before the decimal point, then the zero has no significance other than clarifying the intention of the individual. So if we have this zero that we have right here, it has no significance other than indicating that we intend to write a number without a whole number part. So those zeros show that the numbers definitely have no whole number component. So these numbers have no whole number component. So a zero is placed deliberately there to indicate that. In a whole number that contains no point, trailing zeros are placeholders and may not be disregarded or discarded. So take a look at those numbers. Those trailing zeros cannot be disregarded at all. The zeros are important contributors to the value of the non-zero digits. Zeros that trail the decimal point have no significance whatsoever. If a specified number of decimal places is required, those zeros may be included to make up the number. So those zeros that you have here that trail the decimal point, they have no significance whatsoever, apart from that they contribute to the number of decimal places. Those are the zeros that I'm talking about. Those zeros have no value. They may be included when a certain number of decimal places is requested, or in the case of dollars and cents, in which 2 decimal places are always assumed. If numbers come after the decimal point, trailing zeros enjoy the same status as they did in the previous example. So we have numbers also coming after the decimal point, but zeros are coming after those. Those zeros that I'm talking about, they come after the numbers that are, well, after the digits, the non-zero digits. They are coming after the non-zero digits that are behind the decimal point. The zeros have no value. They may be included when non-zero digits are less than the total number of decimal places required. Their job is to add to the number of decimal places. We are going to be taking a look at significant figures. When writing a number to a number of significant figures, the leftmost, which is the leftmost non-zero digit, is the most significant digit. It has the highest value in the entire number. Good. Now, this is the leftmost digit, but it is not the leftmost non-zero digit. This one is the leftmost. This one is the leftmost non-zero digit. It is the most significant digit. And this one is the most significant digit, the leftmost non-zero digit. It has the highest value in the entire number. The arrows show the most significant digit in each case. So the arrows are pointing to the most significant digits in the entire number. When writing a number to a specified number of significant figures, go to the digit in question and check the digit to the right of it. If that digit is greater than or equal to 5, add 1 to the specified digit. The digit to the right is always the next in order of significance, and we'll see that playing out very graphically in a short while. Write the given number correct to 3 significant figures. So that is the number that we're going to be writing to 3 significant figures. Locate the third digit in order of significance by counting from the left. So we're going to come here. In order of significance, 1, 2, 3. So this is the first, this is the third one. So we're writing to 3 significant figures. This is the third one. So there we have it. Check the number that is next in order of significance. That is to the right. So we're going to check that one. Yeah. The digit is not greater than or equal to 5. That is, the one, this is our position that we are focusing on. The one to the right is not greater than or equal to 5. We do not add 1 to the 8. The 8 remains, and the 4 is replaced by a 0, which is, in fact, a placeholder. So this is our third most significant digit, and we are focusing on it. Then we take a look at the digit that is next in order of significance, which is the one to the right of it, which is the one that you see marked with that blue arrow. Check to see if it is equal or greater than 5. If not, it is replaced by a 0. If it is, then we are going to add 1 to the 8. But in this case, it is 4, so we are just going to replace it with a 0. Now, on the next slide, we'll have every single thing outlined in greater detail. Now, we are going to write the given number correct to 3 significant figures. 3 significant figures. So what do we do first? Oh yes, we take a look and ensure that we highlight that 3. So we are going to the third significant digit. That's what we are going to identify first. Locate the third digit in order of significance by counting from the left, which is the left is the most significant digit. That is where we're going to count from. So there we have it. That's the third most significant digit. Now we are going to check the one. Check the digit that is next in order of significance, which is to the right of it. That one. So what do we do next? The digit is 7, which is greater than 5. We therefore add 1 to 6. So we need to add 1 to 6. Right, that we're going to have 7. The other digits to the left are not affected and return as they are. Like that. And a placeholding 0 is included, maintaining the size of the number. Of course, we need to include that placeholding 0 for reasons we will see in a minute. Without the placeholding 0, the approximation would have been 547. And that is a way off from the original that we have, 5,467. So we have 5,467, and we would have approximated that to be 547. That is not going to be a good approximation. So the placeholding 0 is very important. We're going to write that same number that we did before, this time to 2 significant figures. And we are highlighting the 2 to ensure. Right, so we highlight the 2, showing that we are looking at the second most significant digit. Locate the second digit in order of significance by counting from the left, which is, the left is the most significant digit, so we are going to do that. So we have done that. Our next task is to check the digit that is next in order of significance. That is to the right of it. The digit is a 6, greater than 5. We therefore add 1 to 4. So we need to add 1 to 4 because this is greater than 5. Right. Then the 1, the other digit to the left, is not affected and return as it is. That is the 5 that we have over there, returns as it is. And of course, what do we need? Zeros are used as placeholders in order to maintain the order of the number, which is the relative size of the number. Without the placeholding zeros, the approximation would have been a mere 55. This would have been a ridiculous approximation of 5,467. We're going to write that one now, which is the same one, to correct to one significant figure. So we are going to be looking at the most significant digit this time. So locate the first digit in order of significance. It is the leftmost digit. That one. Check the digit that is next in order of significance, which is to the right of it. Right. The digit is a 4, less than 5. We therefore do not add 1 to 5. So we're not going to add 1 to 5. So the 5 goes back as it is, and what? Zeros are used as placeholders in order to maintain the relative size of a number. By now, the necessity of including placeholders should be understood, and this knowledge should be applied in all other circumstances where necessary. So write the given number correct to 3 significant figures. Locate the third digit in order of significance by counting from the left, which is the most significant digit. Check the digit that is next in order of significance. That is the one to the right. The digit is a 9, which is greater than 5. We therefore add 1 to 9. Adding 1 to 9 results in 10. We write 0 and carry 1. This will happen in the other 9 until the 1 is eventually added to 5. So we are going to add 1 here. We are going to add 1 to this 9, 10. So 0 carry 1. and then 9 plus 1 is 10, 0 carry 1, and that is what will happen. At the end, placeholding zeros are included in order to maintain the relative size of the number. The answer looks more like one significant figure rather than three significant figures. As a matter of fact, that is the same answer that would have been received if one significant figure were required. The answer to two significant figures is also quite remarkable. Write the given number correct to two significant figures. 2. Locate the second digit in order of significance by counting from the left. Check the digit that is next in order of significance, that is the one to the right of it. The digit is a 9, which is greater than 5. We therefore add 1 to 9. So we are going to have our same situation. Adding 1 to 9 results in 10. We write 0 and carry 1. That will be added to the 5. And then placeholding zeros are included in order to maintain the relative size of the number. Notice that writing the number to three and two significant figures results in the same answer. The answer would have been the same if four significant figures were used. This is a quite probable feature when working with significant figures. Write the given number correct to three significant figures. Locate the third digit in order of significance by counting from the left. And at the left, we have the most significant digit. There we go. Check the digit that is next in order of significance. That is the one to the right of it. The digit is an 8. So the digit is an 8, which is greater than 5. We therefore add 1 to 5. The other digits to the left are not affected and return as they are. A placeholding 0 is included, maintaining the size of the number. Notice that the 0 is counted as a significant digit. This one. Notice that the 0 is counted as a significant digit. It cannot be disregarded because it is not a leading 0 nor a trailing 0 that comes after a decimal point. The rule that is generally used in this situation is a 0 that comes between two significant figures is considered to be a significant figure. Write the given number correct to one significant figure. Locate the first digit in order of significance. It is the leftmost non-zero digit. Check the digit that is next in order of significance. The digit is a 5. We therefore add 1 to 9. 9 plus 1 is equal to 10. After writing the 0, 1 is carried to the left, as in normal arithmetic. The trailing 0 beyond the point is unnecessary. The answer may be written as 1. Having trailing zeros in an answer does not make it wrong. Writing a number correct to a specified number of decimal places this time is analogous to writing it to a number of significant figures with two major exceptions. So we are going to be taking a look at decimal places, how to write a number correct to a specified number of decimal places. It is analogous to writing the number correct to a number of significant figures, but we have two exceptions. Let's look at them. All zeros that are to the right of the decimal point are counted in the number of decimal places, whether or not the decimal point is preceded only by a single zero. The highlighted zeros all contribute to the number of decimal places. In the case of 0.50, the trailing zero does not contribute to the value of the number, but it is pertinent to the number of decimal places. So all of those numbers contribute to the number of decimal places. All of those digits that we have there contribute to the number of decimal places. Trailing zeros in typical numbers may be discarded. If they, however, contribute to the number of decimal places, they are retained. The highlighted zeros may be disregarded when writing numbers regularly. They are retained if they contribute to the required number of decimal places. The first decimal place is the first number to the right of the decimal point. Write the given number correct to 2 decimal places. Locate the second decimal place beginning at the first digit to the right of the decimal point. Check the digit that is next in order of significance. The digit is a 9, which is greater than 5, so we therefore add 1 to 4. The other digits are not affected and are included as they are. A placeholding 0 is not necessary because it does not contribute to the number of decimal places nor the value of the number. Write the given number correct to 1 decimal place. Locate the first decimal place, the first digit to the right of the decimal point. Check the digit that is next in order of significance, the one to the right. The digit is a 4. We therefore do not add 1 to the 8. The digits to the left are not affected and return as they are. As usual, trailing zeros after a decimal point is not necessary. Write the given number correct to 3 decimal places. Locate the third decimal place 3 digits to the right of the decimal point. Check the digit that is next in order of significance. The digit is 7, which is greater than 5. We therefore add 1 to 9. Nine plus 1 is equal to 10. After writing the 0, the 1 is carried. The other digit is also a 9, and the same thing will happen until 1 is added to the 0. The 6 is not affected by the operation, and it goes back as it is. The trailing zeros would have been discarded under normal circumstances. However, the necessity of completing the required number of decimal places causes them to be indispensable. So we cannot get rid of those 2 trailing zeros because we need 3 decimal places. 3 decimal places are required from what we have here. So the statement says, write the given number correct to 3 decimal places, so we have to have 3 decimal places in our answer. just let us take a look at standard form. Another name for standard form is scientific notation. So before examining the formalities of scientific notation, let us take a look at how results are obtained in standard form. Let us say that we want to write this number with a decimal point at another location. That is where we have placed it, all the way behind the 4 and the 7 that are the most significant digits. According to the new location of the point, we have evidently made the number smaller. This means that we have divided the original by a power of 10 that is determined by the number of decimal places. So we have divided by a certain power of 10. That is why this number appears smaller than the one that we had before. Making the number smaller by 4 decimal places means that we have divided by 10 to the power of 4, or 10,000. Dividing the number by 10,000 and leaving it like that is unfair. We therefore need to use a power of 10 that will restore it to its original value. The movement of the point is dividing by 10 to the power of 4. We therefore need to multiply the new number by 10 to the power of 4 in order that it will have the same value as the original. So, by moving the point, we have divided the number by 10 to the power of 4. So if we want to restore it to its original state, we need to multiply by 10 to the power of 4. And that is what standard form is all about. So what we had there before, now that we have moved the point, in order that the number will be the same, the one that we have just created, is going to be the same in value as the one that we had before, we have to multiply by 10 to the 4. Because by writing this number like this, it means that we have divided by 10 to the power of 4. In the previous example, we have seen where a big number was made small by dividing by a power of 10. The number was returned to its initial value by multiplying by that same power of 10. Let us write this number with the decimal point at another location. So let us put the decimal point, say, right behind that 5 there. So we have now 5.47. Obviously, the number was made larger. The decimal point was moved 5 places to the right, and leading zeros were removed. This constitutes a multiplication by 10 to the power of 5. The number is made larger, so we are sure that we multiply by 10 to the power of 5. This is not hard to see, as the original number was a very small decimal fraction. The new position of the point has given it a whole number component. Therefore, we are in no doubt that the process was multiplication. So we are sure that we multiplied. We multiplied, moving the decimal point 5 places. That means we multiplied by 10 to the power of 5. We now need to restore the number to its original value by dividing the number by 10 to the power of 5. So we are going to divide the number that we have now created by 10 to the power of 5 so that it can be restored to its original value. How was it created? By multiplying by 10 to the power of 5. So how do we restore it to its original value? Dividing by 10 to the power of 5. Let us divide a general number, say x, by 10 to the power of 5. That's what we have. According to the laws of indices, a number may be written as its reciprocal with the sign of the power change. So when we have a number like this with 10 to the power of 5 in the denominator, that may be written as 10 to the power of negative 5 in the numerator. So that is what we have gathered from the laws of indices. So if you are going to be forgetting the stuff that you learned before, it will come back and haunt you. So it is the same thing as x times 10 to the power of negative 5. The new number accompanied by its adjustment is 5.47 times 10 to the negative 5. And that is the whole principle of writing a number in standard form. When writing a number in standard form, the point is relocated so that there is only one non-zero digit in front or to the left of the decimal point. Now, we are going to write this in standard form, so this point is going to come so that only 6 is to the left of the decimal point. So what do we say? Count the number of places that the decimal point is moved in order to have one non-zero digit in front or to the left of the decimal point. That is where we are going to place our decimal point, and we have counted 3. The point is moved 3 places to the left. The number is therefore divided by 10 to the power of 3. We need to recover the original value of the number by multiplying by 10 to the power of 3. So when we move the point, that constitutes a division by 10 to the power of 3. Because we have made the number smaller, so we are sure that it's a division. So we need to multiply by 10 to the power of 3, that it might be returned to its original value. We may consider a number that initially has a digit or set of digits greater than 0 to the left of the decimal point as a large number. As a rule, we may say that numbers that are initially large should be accompanied by a positive power of 10. That is, after we have written it in standard form, any number that is classified as a large number, like this one is a large number because it has non-zero digits coming before the decimal point. So these digits precede the decimal point. So this is considered to be a large number. At the end, a large number should be accompanied by a positive power of 10. The number of places that the point moves will tell us the size of the power. So if it moves by 3, we know that the size of the power is 3. When writing a number in standard form, we are going to repeat that the point is relocated so that there is only one non-zero in front of or to the left of the decimal point. Look at this one. We have to relocate this point all the way down here so that there is only one non-zero digit in front of that decimal point or to the left of that decimal point. Count the number of decimal places that the decimal point is moved in order to have one non-zero digit in front of it. The point is moved 5 places to the right. The number is therefore multiplied by 10 to the 5, or 10 to the power of 5. So that is what we have. We need to recover the original. So we need to recover the original value of the number by dividing by 10 to the power of 5. Now, relocating the point is equivalent to multiplying by 10 to the power of 5. Therefore, we have to recover the original value of the number by dividing by 10 to the power of 5. Of course, dividing by 10 to the power of 5 is the same thing as multiplying by 10 to the power of negative 5. We may consider a number that initially has only a single 0 to the left of the decimal point as a small number. As a rule, we may say that numbers that are initially small should be accompanied by a negative power of 10 in the end. The number of places that the point moves will tell us the size of the power. So this is considered to be a small number. Why? Because the only number that is to the left of the decimal point is a 0. So we classify that as small. Therefore, in the end, the answer should be accompanied by a negative power of 10. So large numbers at the end are accompanied by positive powers of 10. Small numbers at the end are accompanied by negative powers of 10. The number of places that the point moves, of course, will tell us the size of the power. If the point moves by 6 places, we know that it's going to be either positive or negative 6 that we're going to use for the power. So now we are going to write that number in standard form, and we are going to count the number of decimal places that the decimal point is moved in order to have only one non-zero digit to the left of it. The point is moved 2 places to the left. The number is therefore divided by 10 to the power of 2. We need to recover the original value of the number by multiplying by 10 to the power of 2. Count the number of places that the decimal point is moved as usual. Just 1. The point is moved 1 place to the right. The number is therefore multiplied by 10. We need to recover the original value of the number by dividing by 10. This is equivalent to multiplying by 10 to the negative 1. The counter started at 0 in order to show that the original position of the point is not counted. Students may begin at 1, and by doing so, they must be at the first position that the point is moved to.